So the title of my talk is Quasistationary Evolution of the Magnetic Field in the Course of Neutron Stars. And this work is made in collaboration with Elena Kantor and Dima Afingame. So let me set the problem first. The magnetic field in neutron stars ranges from 10 to the 8, 10 to the 16 Gauss, and to interpret observations from the very diverse classes of neutron stars, it's important to study the evolution of the magnetic field with time. And here we concentrate on the evolution of magnetic field in the neutron star core. So what should we know to model the evolution? According to Faraday law, we need to know the electric field. And this electric field in the core, for example, it depends on many different quantities, for example, on particle velocities, on chemical potentials, perturbations of chemical potentials, and on magnetic field itself. And it's important to stress that these quantities also determined by the magnetic field. So it's a complex problem to determine all these quantities. So our aim is for a given specified configuration of the magnetic field to calculate accurately all the quantities that determine dB over dt, which means that we are going to prepare a basis for modeling the magnetic field evolution in the core. So there are quite a lot of works in this direction, and some of them are listed here. And they mainly follow the approach to this problem pioneered by Galbraith and Reisenegger in 1992. And the most advanced work developing the ideas of GR92 is the recent paper by Passamonti et al. And although these papers are very enlightening, the validity of some approximations made in these references remains unclear to us. And so our purpose was also to check these approximations and to think on them. So for simplicity in this talk, I consider the simplest possible core composition. Neutron star core composed of neutrons, protons, and electrons. I neglect the superfluidity and superconductivity effects. There is also no general relativity effects. And I assume that our star is actually symmetric, so the magnetic field just depends on r and theta coordinate. Then the general equations which govern such a relatively simple system are written here, and they consist of the momentum equation for each particle species, for neutrons, protons, and electrons. Here, U(a) is the velocity of particles, mu is the chemical potential, and for example, this is a term due to friction forces between different particle species. So the second equation is the continuity equations for each particle species. And here, this is a source due to non-equilibrium beta processes, which are induced by the magnetic field. Magnetic field perturbs the system out of beta equilibrium. So the next equation is just a Poisson equation for gravitational potential. This is a Faraday equation, this is an Ampere equation, and this is a quasi-neutrality condition. So these equations are still difficult to solve, and we need to make some approximations. So these approximations are the same as in the classic paper by Galbraith and Reisenegger. So first of all, we neglect small nonlinear terms in these equations, this one. The second, we will use we adopt Cowlin approximation, which means that we neglect the perturbation of gravitational potential. Third, and the most important thing, is we assume that the system is quasi-stationary. What does this means? That the magnetic field, we assume that magnetic field is the only driving force that distorts the system from equilibrium. This allows us to neglect time derivatives in all respective equations, in momentum equation and in the continuity equation. So the resulting equations are much simpler. And these equations contain also the total force balance equation, which is just the statement that gradient of total pressure equals to the Lorentz-Forens density. So these equations can be solved, and it's suitable to discuss the solution in terms of these quantities. The first is perturbation of neutron chemical potential induced by the magnetic field. The second quantity is chemical potential imbalance. because of this quantity, we have non-equilibrium beta processes in the core. And the third quantity is the flow velocity of the fluid as a whole. And the fourth quantity is the diffusion velocity of species A, which is just relative velocity of particles A with respect to the flow of the fluid as a whole. So it can be shown that knowledge of these quantities fully determines evolution of the magnetic field, and we calculated them all except for the toroidal velocity, flow velocity of the fluid, for which we derived a differential equation, but still haven't obtained a solution. So let us discuss the solution. First of all, let's discuss the chemical potentials, neutrons, and imbalance of chemical potentials. So they can be found from the total force balance equation. The solution, this equation can be solved, and the solution is presented here in the matrix form. Here we see the components of the Lorentz force density, and all these guys are known, and only interesting quantity here is the function zeta, which is unknown, but it can be shown that it's unambiguously defined from the requirement of regularity of the flow velocity u at the magnetic poles at any coordinate area. This requirement gives us a differential equation for the function zeta. So, in fact, we know how to calculate perturbed chemical potentials. Now, the interesting property of this solution is that if we expand these chemical potentials in Legendre polynomials, then all the components in this expansion with L larger or equal than unity are fully specified by the magnetic field, which means that they are, for example, do not depend on temperature. This follows just from the form of the solution, and they do not depend on this zeta function. So this is in contrast to the solution obtained previously, for example, in the paper by Goldreich and Reisenegger, in which all the components of perturbed chemical potential depend on temperature. So what is the reason for such a discrepancy? We believe that the results are different because of the approximations made in the previous works. For example, Goldreich and Reisenegger assumed from the very beginning that neutrons are immobile. In turn, Passamonti et al. Assumed that either baryon velocity is zero or the matter is non-stratified. So our analysis shows that these assumptions, and I will talk about it a little bit later, that these assumptions are not actually valid, and baryon and neutron velocity are not small and can be neglected generally. So, to calculate numerically chemical potentials, we need to specify, and all the quantities, we need to specify, of course, the magnetic field. And we choose the same models of the magnetic field as those used by Passamonti in their paper. And this allows us to compare our results with theirs. So here I present an example, numerical results for the perturbed imbalance of chemical potential. Here I show our result, and this is the result taken from the paper by Passamonti et al. Here you see a half of the star, and by different colors we show the magnitude of delta mu in units of temperature. And temperature here is taken like this, and the magnetic field at the magnetic poles is 10 to the 14 Gauss. So you see that generally the magnitude of delta mu and the structure of the plots are very different. This is so we discussed the perturbations of the chemical potentials, and next let's discuss the diffusion velocities. They can be found from these three equations, provided that this delta mu n is already calculated. So the first equation is just the statement, is the force balance equations for neutrons. It's just the statement that gradient or partial pressure of neutrons is balanced by the friction force between neutrons and protons. And these we neglect here the friction force between neutrons and electrons, which is much smaller. The second equation is simply Ampere law. And the third equation just follows from the definition of the flow velocity of particles. So these three equations allow us, linear equation, allow us to calculate diffusion velocities. What? So, and it's interesting to compare our results with those of Passamonti because, however, instead of the diffusion velocities, these authors calculated the so-called ambipolar velocity, which is defined like this. It's proportional to relative motion of protons with respect to neutrons. So here we present our result for the ambipolar velocity, and this figure is taken from the work by Passamonti. Here arrows shows the direction of the ambipolar velocity. It's half of the star, and magnitude. Here I plot the logarithm of ambipolar velocity in kilometers per megayear. So different colors show this quantity. And you see that by comparing these figures, you see that the topology of the ambipolar velocity is very different, and ambipolar velocity calculated by Passamonti et al. Is smaller by a few orders of magnitude, which is quite a large discrepancy. Okay, so we discussed these three quantities, and then the most interesting one, which was not calculated up to now in the previous works, is the flow velocity of the fluid. So how to determine it? First of all, let us determine the R and theta components of the flow velocity. They can be determined from the neutron and proton continuity equations. Here are they, and we can solve them and determine UR and divergence of U. This is again a linear equation as a functions of already known quantities, as functions of diffusion velocities and perturbations of chemical potentials. So we know them, and since our problem is actually symmetric, there is no phi component in the expression for divergence of U, phi component of the velocity. So we can determine from these guys theta component, which is given just by this integral. So we have an analytical expressions for the R and theta components of the fluid velocity, and phi component will be discussed a bit later. So here I present the results. Here I show R and theta components of the fluid flow velocity in units of 10 to the minus 12 centimeters per second. And for comparison, I also present the diffusion velocities for neutrons and for protons. Again, colors show the magnitude of the diffusion velocities, and arrows show the direction. And you see from these figures that the rather important result that the flow velocity is substantially larger than diffusion velocities. And this clearly indicates shows that approximation of vanishing U is incorrect, in our opinion. So, and what about toroidal component of the flow velocity? How could we determine it? The idea is to look more carefully at the quasi-stationary balance equation. We already saw it. It depends on the perturbations of chemical potentials. But they are, because our problem is quasi-stationary, they are the functions of R and theta only, which means that the gradient of these chemical potentials can't have a component along the phi. What does it mean? This means that magnetic field configuration should be such that the phi component of the Lorentz force vanishes, because it cannot be compensated by the gradients of chemical potentials. Okay. But the magnetic field changes with time. For example, it dissipates. So this means that to maintain quasi-stationarity in the course of field evolution, we have to require that not only phi component of the Lorentz force to be zero at any moment of time during its evolution, which is equivalent to condition that the time derivative of this force vanishes. So if we employ Faraday equation and the definition of the Lorentz force density, then we can transform this condition to the following form. And here E is the electric field in the laboratory frame, and it can be generally related to the electric field in the comoving frame by this well-known formula. And E comoving is the electric field in the frame in which fluid flow velocity vanishes. So comoving frame, electric field in the comoving frame we already calculated because it's known functions of perturbations of chemical potentials and diffusion velocities. We know it. So we can substitute this expression here and obtain a differential equation for toroidal velocity Phi, which still to be solved because it's a rather complex equation. So we are working on its solution now, but don't have the results. So I'm finishing. We have calculated all the quantities except the toroidal component of the flow velocity that allow us to self-consistently follow the quasi-stationary evolution of the magnetic field in the neutron star core. So we have all ingredients to follow this evolution for the first time. Our results differ quantitatively from the results available in the literature, e.g. in these papers. In particular, the flow velocity turns out to be non-negligible, larger than the diffusion velocities. And this is contrary to what was assumed in the previous works. The toroidal component of the flow velocity plays an important role in maintaining the quasi-stationarity of the system. So it guarantees the quasi-stationarity. The approach presented here can be extended to include the effects of superfluidity and superconductivity, additional particle species, non-axisymmetric magnetic field configurations. And more details can be found here, and we are now preparing one more paper on this. So there are also so our nearest plan is to calculate Phi, toroidal velocity, try to model the quasi-stationary magnetic field evolution, and in this way there is some problem. We need to think on how the presence of the crust will affect the results, and probably to apply the results to magnetars. Thank you.
Thank you.
You mentioned something about the assumptions of previous authors, but actually at such temperatures protons are superconducting, so the assumptions of the present paper is just incorrect.
No, the point is the degree of superconductivity or superfluidity depends on the magnetic field. For example, in magnetars, if you take 5 times, for example, 10 to the 15 Gauss, then
you mentioned 10 to the 14.
Yes. I from the very beginning, I said that we consider the simplified simple problem just because there are incorrect results, as we believe, even for this problem. So before to move forward, we need to understand what is what in the simplest situation.
And it's not surprising that your results do not coincide with the correct ones.
No, because these authors also consider non-superfluid and non-superconducting matter.
But someone considers superconducting.
No. We compare they consider various possibilities, and one of these possibilities, they consider normal matter. I can show the reference during the coffee break.
Yeah. Thank you. More questions?
Yeah, you showed the chemical potential imbalance, but did you also include weak processes, or are they?
Yes, of course.
Yeah, okay.
And I mentioned it. So we include the source in the continuity equations due to beta processes. Yes, and it's a function of this imbalance of chemical potentials.
Okay. More questions? No. So let's thank our speaker again and move to the next one.